In this video, we're going to take a look at exam revision for trigonometric identities and solving trig equations. So what we're going to do for this video here is take a look at 4 exam style questions for trig identities and solving trig equations. Like always, pause the video, have a look at the questions they appear, and then double check that your solution matches what we get on the screen. Other than that though, I don't think we really need anything else here to get started. So let's begin now with question 1. Starting off with question 1 then, we want to find the solutions of the equation root 2 cos x equals 1 in this given interval here for x. Now to start with, I'm just going to write down the original trig equation. So we've got root 2 cos x equals 1. Now, what we want to do here to begin with is isolate cosine x. We need to get rid of the root 2 here in front. So the way that we do that is divide both sides by root 2. On the left-hand side, we get left with the cos x isolated on its own like we wanted. So cos x is equal then to 1 over root 2. So dividing the right-hand side then by root 2, we get 1 over root 2. Okay, should hopefully be nice and straightforward. Now that we've isolated cosine x, we now can take cos inverse of both sides. And what this does is it gives us x here on the left-hand side. So it allows us to solve for x then, which is what we want to do here. So therefore x equal. So x equal then to cos inverse or arc cos, whichever way you prefer to write this. So cos inverse of the right-hand side then, which is 1 over root 2. Okay, like so. So you need to do now is put this into your calculator here. So cos inverse of 1 over root 2. If you do this correctly, what you should get then is 45 degrees. Okay, so we get 45 degrees there. That is my first solution. Okay, now to obtain the remaining solutions here, I'm going to use a cast diagram. Okay, you don't have to use a cast diagram. If you prefer, say, a graphical method, that's absolutely fine. I personally prefer a cast diagram. That's the method I'll use throughout this video. Okay, if I draw out my 4 quadrants here, we'll get something that looks, say, like this. Okay, I've got C in this quadrant, A in this quadrant, S, and then finally T. Okay, now we're working with cosine here, so where is cosine positive? Well, cosine is positive in this quadrant here because all trigonometric functions are positive in this quadrant. So we obtain this angle here, which is 45 degrees. That's what we've just found. So that's 45 degrees. So where else is cosine positive? Well, cos is also positive in this quadrant here. So again, I get this angle, which again is 45 degrees. Okay. So how do we obtain then the next solution here? Well, we consider the cast diagram then. So what we're looking for is the angle that's formed from this line here, which would be our x-axis technically. And we go all the way around until we touch this line here. So what's this angle that's formed? Okay. So if we think about this here and basic properties of angles, so if we were to go all the way around here so we meet the x-axis again, that would be 360 degrees, 1 full revolution, okay, or 1 full turn. So in that case then, if we know the angle in between this line and the x-axis, we do 360 minus this angle. So my next solution then is 360 minus 45, and that would give us 315 degrees there. So we get 315 degrees there. Now, just by looking at the domain then, so the domain here for x is for 0 to 540 degrees. I'm going to be careful here, so I'm going to assume there are more solutions. There might not necessarily be more solutions, but I would assume straight away that there's at least one more solution here. Now, we know that cosine is periodic every 360 degrees. Okay, so it repeats every 360 degrees. So if I've got this solution here at, say, 45 degrees, my next solution then after 315 degrees would be 45 degrees plus 360 degrees. And clearly then that would lie in this domain here. So my next solution, let's just write this down. So my next solution, this is equal to 360 plus 45, and that would give us 405 degrees there. Okay. So the next solution then would be this angle, 315 degrees, plus 360 degrees, because it repeats every 360 degrees. But clearly, if I have 315 degrees and I add 360 degrees to that, this would fall outside of this domain here for x. Okay, it would be larger than 540, so therefore we would reject that solution. And therefore then what that tells us is we have the full set of solutions here for x, so therefore let's write down the solutions. So therefore x is equal then So we've got 45 degrees. We've got 315 degrees. And then finally 405 degrees there. Okay. And there we have it. So that is the solution there to question 1. Moving on to question 2 then, we want to find the solutions of the equation tan of x plus 20 degrees equals root 3 in this given interval here for x. Let me just start by writing down the original trig equations. I've got tan of x plus 20 degrees, and this is equal to root 3. Okay. Now what I noticed straight away here compared to the previous question is the argument of our trigonometric function isn't just say x or theta, it's now x plus 20 degrees. And this does change the working ever so slightly. So the first thing that we need to account for here is the domain. Notice the original domain is for just x, but we're working with x plus 20 degrees. So what I'm going to do here is add 20 degrees through my interval here. So 0 plus 20 is 20. And this is obviously in terms of degrees. So 20 degrees, we then get x plus 20 degrees. Like so. And then for the upper bound here, that would be 540 plus 20. So that would give us 560 degrees there. Okay. So I now look back at the original trig equation here. And I notice that the left-hand side, our trigonometric function is isolated. So we can now just go straight into taking tan inverse of both sides. So if I take tan inverse of the left-hand side here, I get left with x plus 20 degrees. So I get left with the argument here of our function. We get x plus 20 degrees. And that's equal then to tan inverse of root 3. So tan inverse of root 3. So if I put this into my calculator here, what I get then for tan inverse of root 3 is 60 degrees. Okay. That's our first solution there to this equation. Now to obtain the remaining solutions here, again, I'm going to use a cast diagram. So I quickly draw out my quadrants here. Like so. We'll get something that say it looks like this. So we've got C, A, S, and then finally T here. So working with tan here, so obviously tan would be positive in this quadrant here because all trigonometric functions are positive in this quadrant. So this would be 60 degrees then. Okay, that's this solution. Tan is also positive in this quadrant here. This is for, or this T is for tangent. So it's positive in this quadrant here. So we've got this angle, which again is 60 degrees. Okay, so that's 60 degrees. Now, what we're looking for then for the next solution is going from this line here, what would be our x-axis, all the way around until we meet this line here. Okay. So to find that solution, that would be from here to here, which is 108 degrees, plus this angle here, which in this case is 60 degrees. So my next solution then for x plus 20 degrees is 60 degrees plus 108 degrees, that's 240 degrees there. Okay. Now, if we look at the domain again, we're working between 20 degrees and 560 degrees then for x plus 20 degrees. So we know that tan is periodic every 108 degrees. So this would suggest then that we're going to probably have a few more solutions here. Okay. So we go back to the first solution then, 60 degrees. If I add 180 to that, that gives me the 240, so that's fine. We've then got 240 degrees, so if I add 180 to that, what would that give me? Well, that would give me 420 degrees there. Okay, so next solution. So my next solution then is equal to 240 plus 180, and that gives us 420 degrees there. Okay. Now, if I add 180 to this, this would be greater than the 560 here. So we know straight away that that solution would be rejected. It'd be greater than 560, so we just omit that solution. Okay. So what this tells us is we have the full set of solutions for x plus 20 degrees. So x plus 20 degrees, this is equal then to 60 degrees. We've got 240 degrees. And then finally, we've got 420 degrees. Okay. But here we're looking to solve for x. So what I need to do now is subtract 20 degrees off each solution then. So therefore x is equal, like we said, just subtract 20 degrees off each solution. So 60 degrees minus 20 degrees is 40 degrees. 240 degrees minus 20 degrees is 220 degrees. And then finally, 420 degrees minus 20 degrees gives me 400 degrees. Okay, and there we have it. So that's the full set of solutions there for x, and that gives us the solution there to question 2. Moving on to question 3 now, where we have two parts of this question. So let's begin with part A. So for part A, we're given that 2 cos x is equal to sin x, and we just want to find the value of tan x. So very typical kind of opening here to an exam style question on solving trig equations. So for the first part here, this is just based around our trig identities. So what links here, sin x, cos x, and tan x? Well, we know that tan x is equal, or it's identical, I should say, to sin x over cos x. Okay. If we have 2 cos x equals sin x, what that would suggest to me then is if we divide through by cos x here, we should hopefully be able to find the value of tan x. So let's do that underneath them. So for part A, we've got 2 cos x equals sin x, like so. So like we said then, let's divide through by cos x here. So what I'm going to get then is 2 cos x over cos x. And this is equal then to sin x over cos x. Okay. If we have 2 cos x over cos x, they'll just cancel. I get left with 2 there. And then sin x over cos x, like we've said, that is identical to tan x. What we've got then is, therefore, tan x is equal to 2. Okay, so nice and straightforward, the value of tan x is equal to 2. So that's part A done. Now for part B, it says, hence or otherwise, find the values of x in this given interval here for x, for which 2 cos x equals sin x, giving our solutions to 1 decimal place. So very typical kind of exam style question then, a bit of an easier one, but again, pretty typical. So for part B, it is a hence or otherwise. So let me just kind of box this off here just so we don't get kind of confused. Like so. So for part B then, notice this here is the exact same as what we had in part A, and this is why it's a hence or otherwise. So we're going to use our answer in part A to help us answer part B. If we have 2 cos x equals sin x, we want to solve this equation here for this given interval, but we know that 2 cos x equals sin x is just the same as tan x equals 2. This is much easier to work with. So we've got tan x equals 2. So tan x equals 2 then. Well, our trigonometric function here is isolated, so we can go straight into taking tan inverse of both sides. So therefore, x is equal. So x is equal to tan inverse of 2. Like so. So just use your calculator here. So tan inverse of 2. So if I put that into my calculator here, tan inverse of 2, what I get then, and if I give it to 1 decimal place, is I get 63.4. Okay. 63.4 there. That's fine. So that's our first solution. Now, again, you might not need it because we did the previous question, which was also in terms of tan. You might just remember it straight away from the previous question, but I'll do it again just in case you forgot. If we use our cast diagram here and draw our 4 quadrants then, like so. We've got C, A, S, and T. And we know that tan is periodic every 180 degrees. So it repeats every 180 degrees. We've got our first solution here. But this angle is 63.4 degrees there. So 63.4 degrees. My next solution then is derived from the angle that's formed going from this line here all the way around until we meet this line here. Okay. Well, we know this angle here is also 63.4 degrees. So in that case, then the angle that's formed from this line here all the way around would be 180 plus 63.4. So 180 plus 63.4, and that gives me 243.4 degrees there. So 180 plus 63.4, we get 243.4 there. Okay. Now we know, like we said, that tan is periodic every 180 degrees. So if I add 180 to this, it would then fall outside of the domain here for x, so therefore we would reject and omit that solution. Okay, so what that tells us then is we have the full set of solutions then for this equation. Let's just write down these solutions here. So therefore x is equal to 63.4 and 243.4 degrees there. Okay, that gives our solutions to one decimal place, and that gives us the solution there to question 3. And finally then, if we take a look now at the very last question here, question 4, where again we have two parts to this question. So let's begin with part A. So for part A, it says show that the equation 6 cos squared x equals 4 plus sine x can be written in this given form here. So this is a very typical exam style question here. The first part being based around trig identities, and the second part, part B, being based around solving trig equations. So if we start with part A then, like we said, this is based around trig identities. I can see straight away that we have 6 cos squared x here, and we also have 6 sine squared x here. So that would suggest to me that we need to use the following trig identity. So we're going to use sine squared x plus cos squared x is identical to 1. Okay, and from here what we can do is rearrange this and make either sine squared x a subject or cos squared x a subject. Now given that we start with 6 cos squared x here, what I'm going to do then is rearrange this and make cos squared x the subject. I get cos squared x is equal to 1 minus sine squared x. Okay, now we can substitute this into the left hand side then, so we get 6 lots of 1 minus sine squared x. If we do that then, like we said, we get 6 lots of 1 minus sine squared x, like so, and this is equal to 4 plus sine x. Okay, now let's expand this single bracket here. So 6 times 1 is 6. 6 times minus sine squared x is minus 6 sine squared x. And this is all equal to 4 plus sine x, like so. Now I notice straight away that this sine squared x term here is positive, so I'm going to add 6 sine squared x to both sides here to ensure that that is positive. So I get 6 is equal to 6 sine squared x here. We've also got the sine x here, so plus sine x. And we've also got the plus 4 here. And then finally, if we want the required form here, all I need to do now is subtract 6 off both sides. So therefore, 6 sine squared x plus sine x. And then finally, 4 minus 6 gives me minus 2, which is exactly what we need there. And that is all equal to 0. So that's as required there. And that is part A complete. So as required. So that's the first part done. So now for part B, it says hence solve for x between 0 and 360 degrees. This equation here, which notice is the exact same as what we start with in part A, giving our answer to one decimal place where appropriate. So if we're looking to solve this equation here, which is what we start with, but we can write it in this form here, what we're looking to do is actually just solve this equation here. This is much easier to work with than this. Okay, so we've got 6 sine squared x plus sine x minus 2 is equal to 0. Okay, so what we've got here is a quadratic equation, and what I'm hoping is that we can factorize this quite nicely. So if we attempt to factorize here, what would we get? In the first bracket, I'm going to get 3 sine x. We get 3 sine x plus 2. That's my first bracket complete. We then got our second bracket here, and in this bracket, we're going to get 2 sine x minus 1. Okay, and this is all equal to 0. So from here, what we obtain now is 2 separate trig equations. I've got my first equation here that's given by setting this bracket equal to 0. So if I set this bracket here equal to 0, and then rearrange and make sine x a subject, what would we get here? Well, what I'd get then is sine x is equal to minus 2 over 3. Okay, so that's my first equation here. So sine x equals -2/3. We then got a second equation here. So that's obtained by setting 2 sine x minus 1 equal to 0. And again, if we rearrange and make sine x the subject, we get sine x equals 1/2. Okay. And what I need to do now is solve each of these two separate, or each of these trig equations separately. I'm going to solve them separately. Okay. So let's do that. Let's start with this one here. I think this is a little bit easier to work with. So the trig function here is isolated, so we can go straight into taking sine inverse of both sides. So if we do that, what we get then is x on the left-hand side, and that is equal to sine inverse of 1/2. Okay, so if you just put this into your calculator then, sine inverse of 1/2, what do we get here? Well, we simply get 30 degrees. Okay, so that's my first solution. Now to obtain the full set of solutions here, what I'm going to do is use a cast diagram. So if we do that over here, don't need to be perfect. Let's just draw my 4 quadrants like so. I've got C, A, S, and T here. Okay. So we're working with sine here. So where is sine positive? Well, sine is positive in this quadrant here. So this angle would be the 30 degrees. So that's 30 degrees there. And sine is also positive in this quadrant here. Okay. So that's also 30 degrees. But for our second solution then, we obtain that by going from this line here, which would be our x-axis, all the way around until we meet this line here. So to obtain the angle that's formed, that would simply be 180 from here to here, minus the angle in between. So that's going to be 180 minus 30. So that would be 150 degrees there. Okay, so our second solution there is 150 degrees. And that would be the full set of solutions here, because we know that sine is periodic every 360 degrees. However, if I add 360 to either of these two angles here, it would then fall outside of the domain here. It would be greater than 360. Okay, so that's the first of these two trigonometric equations solved. We now move on to this trig equation here. So again, the trig function is isolated. We can go straight to taking sine inverse of both sides. So x is equal to sine inverse. So sine inverse here of -2/3. So again, just put this into your calculator here. What I get now is a decimal answer. So it's not a pretty answer like this, for example, 30 degrees. What I get now is -41.8. So if I round it to one decimal place, I get -41.8 degrees there. Okay. And clearly we wouldn't include this solution here. Okay. It's less than 0. So it falls outside of the domain. However, we can use this answer here to obtain the full set of solutions. So we know that my next solution now, even though this is negative, the next solution would be given by 180 minus this angle here. So 180 minus -41.8. So just be careful here with the signs. My next solution is given by 180 minus this here. So 180 minus -41.8. So what that gives us then is 221.8 degrees there. So 221.8 degrees. Okay. And then is that the full set of solutions here? Well, we need to be slightly careful. So because this angle here is negative, well, like we said before, we know that sine is periodic every 360 degrees. So my next solution here then would come from taking this angle here, -41.8, and adding 360 degrees to that. So this angle here plus 360 -41.8 plus 360, that is equal then to 318.2 degrees. 318.2 degrees there. And that would be the full set of solutions then for this equation here. Okay, we can't obtain any more solutions that fall within this domain. So what I've got now is the full set of solutions here to this equation. Okay, so let me just write down the solutions here then. We're solving for x here. So x is equal then. We've got 30 degrees to begin with. We've got 30 degrees. Like we said, we ignore this solution here. That falls outside of the domain. What have we got next then? Well, I've got 150 degrees. 150 degrees. We've got 221.8 degrees. And then finally 318.2 degrees. Okay. And there we have it. So that is the solution there to part B. And that gives the solution there to the very last question, question 4. And that brings the end of this video on exam revision for trigonometric identities and solving trig equations.